Phase changes, you can measure certain quantities that are involved in phase changes. Let's say that we have a round flask here. It's a nice spherical-ish flask, and it has an opening at the top with a side arm. And we've plugged that opening with a rubber stopper, although I would have used a pressure gauge if it were me based on the experiment they're doing. And then the valve here, they run a vacuum pump, so a nice fancy pump, and it runs and it sucks all the air, all the vapor out from above that liquid. And then we turn off the pump only after we've closed that valve. So if you're familiar with a burette in the lab, for example, the tall, narrow glassware that you use in a titration, you remember that it's closed when the valve, the stopcock they call it, is perpendicular to the glassware, and it's open when it's parallel. So we turn that so it's closed, and at least for a moment there's a vacuum. Nothing above the liquid. No air, nothing. Okay. If we had a pressure thing, it would read 0. If we had an absolute pressure gauge, so not like a tire gauge, which reads 0 when it's atmospheric. Like if we had a real absolute pressure gauge, which would have to know what atmospheric was probably to work, it would be 0 pressure. I know why they don't have a gauge on there, because they don't want to mix you up with a tire gauge or something that doesn't read total pressure, but whatever. Okay, if we could measure the pressure inside that flask that doesn't have any measuring device with it, but let's play along. Over time, we would see the pressure increase. So the graph on the right shows the pressure of the vapor above the liquid at constant temperature as a function of time. So what would happen with the vacuum there is some molecules, a few of them at least, no matter the liquid, a few molecules for any liquid are going to evaporate. It doesn't have to be much. It depends on the liquid. For some liquids, it would be a lot. For some other liquids, it might be very little. But something's going to evaporate. So once you get a few gaseous particles there, we start getting a pressure, right? The volume is not going to change significantly above the liquid, at least to start with. Unless a lot of liquid evaporates, the volume of gas is constant, because the gas is going to occupy the whole space, right? So it's got the whole volume of the flask that's not liquid to occupy. The more molecules that evaporate, the more moles of gas there are. And then P and N are on opposite sides of the ideal gas law, right? If it's constant volume and constant temperature, the larger N is, the larger P is. And PV equal nRT. P and N are the only things that can change, and if there's more N, there's more P. So the pressure would increase. Now, what if in flying around, one of those gas molecules hit the surface of the liquid? If it hits the wall, it bounces off. If it hits another molecule, it bounces off. What if it hits the surface of the liquid? Splash. Liquefies. It condenses. What are the chances of that with only a few gas molecules? Low, right? But the more gas molecules there are, the better the chance of condensation occurring. And what we see is the volume doesn't just increase forever. The volume increases and starts to flatten off. And at some point, the volume levels off. The pressure levels off. It's only the third time today. You think I could get it right. The pressure levels off. And at that point, what's happening at the molecular level is panel B of the cartoon here, where molecules are evaporating and condensing at the same rate. Over a period of time, X number of molecules evaporate, and X number of molecules condense. They're in the gas phase, and they're flying around, and they hit the liquid, and that's condensation, going from gas to liquid. So we have opposite processes, evaporation and condensation, occurring at the same rate. We have a term that describes a system where opposite processes are occurring at the same rate, right? It's a word that starts with E that people thought they were done with, that I'll duck if people are going to throw things at me, but I already wrote it down. It's the E word, right? It's equilibrium. This is reached equilibrium, where there is evaporation, there's also condensation, but they're occurring at equal rates, so you don't notice any net change. So the pressure levels off. This pressure we would simply call the vapor pressure. That would be the y-axis value of the flattened off line there. When it flattens off, we measure that pressure. That's the vapor pressure of this liquid at that particular temperature. If we increase the temperature, we would increase the vapor pressure. That's the next thing we got to deal with. But at constant temperature, the vapor pressure of the liquid is a certain value. What if we opened the flask? The flask is closed. It reaches equilibrium. Now, what if you did this in an open dish? What if you had the same liquid at the same temperature in an open dish or beaker or something? It would also have a vapor pressure. It would have the same vapor pressure at the temperature. It would have the same vapor pressure. But being an open dish, once those molecules evaporate, do they stick around to reach equilibrium? If it's open, they can't, right? If it's open to the air, the molecules get away. So they're not there to condense. And so it keeps evaporating in an attempt to try to reach equilibrium, which is going to be futile because it's not a closed system. But Le Chatelier's principle would say, oh, the concentration of gaseous has decreased, I will produce more. This is why a puddle, even on a cold day, it's cold out, pour some water on the sidewalk in a shadow, eventually it evaporates. Now, how does it evaporate if we're below the boiling point? We're not at 100 degrees Celsius. You say, well, water shouldn't evaporate. It's not 100 degrees Celsius. It evaporates because water has a vapor pressure. Even at a cold temperature, even just above 0 degrees Celsius, it has a vapor pressure. So in an open system, this won't reach equilibrium. Eventually, all the molecules have a chance to evaporate. So in a closed system, you get this equilibrium. In an open system, you can't. But the vapor pressure is the same either way. It's a variable that depends on the temperature. If we increase the temperature, we increase the vapor pressure. So the next cartoon, and that was figure 12. I almost called that first one there that we were looking at a moment ago. I almost called that figure 12.5 earlier. It's not, it's ordinals, not decimal numbers. It's 12.5. This is 12.6 figure of about temperature. We've seen figures like this before. Okay, you've seen it in gas law chapter with kinetic molecular theory. We've seen it with chemical kinetics, and we talk about increasing the temperature increases the rate of reaction because more molecules have enough energy to react. This is really very similar to the kinetics idea. Just the enough energy is a different thing. Instead of worrying about enough energy to react, what we're worrying about is enough energy to vaporize. It's not exactly the same, but it's like the idea if you're familiar with rockets and spaceships and stuff, escape velocity. The huge payload rocket that took off, and the most spectacular part was landing afterwards, right? But to escape into space, a rocket has to have, space shuttle, whatever, they have to have a so-called escape velocity. It's not exactly the same thing. Here we're not talking about gravity holding something back. We're talking about the forces between the molecules that have to be overcome. It's not exactly the same thing, but there is one similarity in that there's a minimum speed. In order to evaporate, the molecules have to have this speed, which is on the x-axis, to have enough kinetic energy. The x-axis is not, and it's a little annoying. I find that annoying. It's that the x-axis is speed, and then this arrow says kinetic energy needed to overcome. The x-axis is not kinetic energy, it's speed, right? That's actually a mistake, and I've complained about it before, and it'll never get fixed. That's the speed that corresponds to the kinetic energy. It seems nitpicky, but kinetic energy is 1/2 mv squared, right? That depends on the speed. But if the x-axis is speed, that's not a kinetic energy per se, it's a speed. That's related to the kinetic energy. Also confounding this is the fact that they're using speed and the symbol U for speed. Kinetic energy involves velocity, which is a vector, not a scalar. U is the quantity part. It's not a big deal. But when it says kinetic energy, just be aware that it really shouldn't say that literally. It should say the speed corresponding to the kinetic energy, because this x-axis is speed. So we see that at hotter temperature T2, the orange curve, the distribution of speeds is flatter and pushed to the right. And if we had an even hotter temperature, T3, that was even hotter, it would be more flat and more squished to the right. It's just a cartoon. You can figure this out with an equation. If you pass P-Chem and start honking your horn, there's an equation. You can graph this very carefully depending on the substance. But we see at the warmer temperature, more shaded area here, more molecules have a high enough speed that corresponds to the kinetic energy you need to escape into the gas phase. So that figure's got its issues, but it's not too bad. So warmer temperature for the same substance, higher vapor pressure. The figure 12.7 shows, here's the curve for water. The blue line is water. And the curve for water here shows that at 20 degrees Celsius, one more bump, there we go. At 20 degrees Celsius, the vapor pressure of water is about 20 torr. The y-axis is vapor pressure in torr. So those are convenient units. It's just a coincidence that it's 20 at 20. If you have Celsius temperature and torr for pressure, the vapor pressure at 20 is about 20. If it were Kelvin temperatures and atmospheres for pressure, the numbers wouldn't be the same, right? It would be something else. So that's fine. It looks like it's about an exponential curve. It is actually. There's an equation for this. We're not that worried about it at the moment. We can eventually see it sometime, but it's an exponential function, it turns out. That depends on the heat of fusion, among other things. So there's an equation with either an exponential or a log, depending which way you're doing the math for this. So the vapor pressure increases faster the higher the temperature goes. And we see that it increases at 100 degrees Celsius. The vapor pressure of water is 760 torr, 760 torr. We're familiar with that, right? That is 1 atmosphere. And that is a familiar temperature for water, right? What do you know about 100 degrees for water? It's what we call, usually we say, is the boiling point, right? Now, this is a thing where, again, it's something that you can be overly technical and paranoid about. So we're going to mention it, but we're not going to run around correcting everyone else in our lives necessarily. The temperature known as the boiling point is the temperature at which the vapor pressure equals the external pressure. Now, we live our lives mainly at about 1 atmosphere. So the external pressure in our lives is usually 1 atmosphere. So the familiar boiling point of water is 100 degrees Celsius. Now, is it exactly 100 degrees Celsius here in this room at this moment? Not exactly, right? We're above sea level, but not by a ton. Even just locally, I mean, right up the street from my house on the topographic map is the contour line for 1,000 feet elevation in Fairlawn. But there's places at Lake Erie are closer to 500 and something, right? There's hills and valleys. At the airport in New Orleans, the elevation is 4 feet above sea level. So we know that altitude has an effect on the atmospheric pressure on average. The atmospheric pressure is higher in New Orleans on average because you're at a lower elevation. There's more atmosphere above you than, say, in Denver. You're a mile up, little less atmospheric pressure, not by a ton, but it does affect the boiling point somewhat. So when we say the boiling point of water is 100 degrees Celsius, what we're actually talking about is the so-called normal boiling point. The normal boiling point is the temperature at which the vapor pressure equals 1 atmosphere. And so, for example, the normal boiling point of water is 100 degrees Celsius. So if someone just says the boiling point of water is 100 degrees Celsius, they are technically not fully correct, right? They should either say the normal boiling point of water is 100 degrees Celsius, or the boiling point of water is 100 degrees Celsius at 1 atmosphere. However, if you ran around correcting people about that all the time, it would get really annoying, and I am not going to feel responsible for any black eyes or bloody noses or anything caused by running around like a grammar Nazi on Facebook correcting people about the normal boiling point. Don't do it, okay? It's really annoying. Let it go. Save it for Jeopardy, okay? So we know that there's a normal versus, and it's not abnormal, it's just normal versus any other boiling point. That's fine. We looked it up during class. It came up. Someone said, what about, we're talking about like Mount Everest. The atmospheric pressure, they looked up the atmospheric pressure at the top. They looked up the boiling point, actually, and then we figured out what the rough atmospheric pressure would be. Now, I've managed to forget the numbers again, but I wrote it down earlier. Let's see. Is this copy 2? That must be just plain. Where's that number written down there? Yeah, it was about 70 some. There it is there. So I wrote it down earlier. Yeah, so 70, it was like 73 or 72 degrees. And so we could use that graph. We could say, all right, if water boils at 72 degrees from this graph, we can read that the atmospheric pressure is about 250 torr. And then someone Googled that, and what do you know? It was about 250 torr. So that's a pretty useful graph, actually. If you know the atmospheric pressure, you can predict the boiling point of water at that temperature. Can you boil water at room temperature? Sure. You just got to lower the pressure. I've seen someone do this. I've literally seen someone do this in a lab. It was a mean trick. They had the round bottom flask and the vacuum pump and everything. They put water in the flask, and they ran the vacuum pump, and they got the pressure in the flask above the water down to about 20 torr. And the water began to boil at room temperature, because the external pressure over the water equaled the vapor pressure of water at that temperature, about 20 torr. And then a friend happened to come in who didn't know about all this stuff in a lot of detail, and they said, "Oh, I was just boiling some water. Hang on, I'll take that off." And they reached over and grabbed it with their hand and went, "Ah, just kidding." And their friend was really annoyed. It was a cute joke, but it was boiling water, but at room temperature, because the pressure was low above it. So. Atop Mount Everest, your 3-minute egg will take 5 or 6 minutes or more to cook, because water boils at a much lower temperature, and it's not providing as much heat. And to cook the egg, you got to provide enough heat, so you got to cook it longer. It's in between in a place like Denver. It's lower temperature, but not 72 or something. It's in the 90s. So can you boil water higher than 100? Sure. You just have to keep a closed vessel with higher pressure, a pressure cooker. If you have a pressure cooker in your kitchen, the idea of that is to boil water above 100 degrees Celsius. You increase the pressure so it boils at a hotter temperature, and you get that liquid water at a higher temperature, and you can speed up the cooking. That's one annoying thing about this graph being cut off where it is that it would be cool to see that line keep increasing, because it does increase if you can increase the external pressure. You can increase it. So, okay, that's water, the blue line. There are a couple other vapor pressure curves here, and we'll have to get back to them. We'll mention them a little bit later, and then it rolls into the next class as well. Water, of course, as we know, is H2O. Both H's are bonded to O. Ethanol, or ethyl alcohol, involves an ethyl group, that's C2H5, bonded to oxygen, bonded to hydrogen. And then diethyl ether involves 2 ethyl groups, bonded to oxygen. Cannot get that right today. Okay, C2H5. Ethyl is C2H5, the ethyl group. Is 2 carbons, then that's bonded to the oxygen, enough hydrogens to fill the octet rule. They're sort of cousin molecules in some ways, right? Each oxygen has 2 lone pairs. I didn't bother drawing them, but they're there. The oxygens are tetrahedral in geometry generally, 104-degree angles because of the lone pairs. They're sort of cousin molecules. The water has 2 hydrogens. The ether has 2 ethyl groups. The ethyl alcohol has 1 of each on the oxygens. But they're sort of cousin molecules in a lot of ways. The ethanol and water at 20 degrees Celsius have similar vapor pressures. The ethyl alcohol has a higher vapor pressure. It's about 50 instead of 20. But look at the vapor pressure of diethyl ether. It's like, 475 or something. It's hard to read sig figs on this graph. A lot higher vapor pressure at the same temperature for the ether. Why? It must be easier to separate the ether molecules from each other than water molecules at the same temperature. That's something that we're going to barely start today, and that's a tease for the week after spring break. But that shows that not all things have the same vapor pressure at the same temperature. The structure of the molecule comes into play, and the forces between the molecules are what's important. So we're going to mention a little of that today, and then it's going to be a tease for the next time. Now, the blue curve, scrolling the wrong way there, the blue curve for water, that is part of a larger graph, actually. That vapor pressure curve for water is part of a larger graph called a phase diagram. On the right, we have the phase diagram for water, and here's the blue curve. It actually didn't even go past 100 degrees Celsius, right? The part of the blue curve that's shown on the previous page is probably actually only down to about there, right? But the blue curve, that part of the blue curve is on the previous page in that cartoon. We can see it actually goes a lot further than what was shown on the previous page. The blue part is just the part we could see in the other graph, but that's the same curve. But a phase diagram shows for any combination of temperature and pressure what state of matter the substance would be. And so there are regions where you have a solid, a liquid, or a gas at low pressure you have a gas, no matter the temperature. If you have somewhat higher pressure at low temperatures, you have a solid. At high temperatures, you have only a gas. At intermediate conditions, you can have a liquid. So most phase diagrams look like one of these. I'm going to skip water for a moment and go to the one on the left, because water, it turns out, is actually a little bit weird in a couple of respects. So I'm going to look at the other one first, actually, for CO2, because CO2's phase diagram is a little more well-behaved as far as being typical. So here's CO2's phase diagram on the left. The solid at lower pressures and colder temperatures. The gas exists at even lower pressures, even if the temperature is very cold, the liquid in the middle. There's a line between the solid and the liquid. If you're on that line, you could have equilibrium between the two phases. Let's say that I had CO2 at this point here, where the X is, and I heated it up at constant pressure. So that would be moving directly to the right. Okay, heating at constant pressure would be moving to the right. Okay, fine, move to the right. It would melt, right? It would be solid, then it would turn liquid. Oh, okay, that's fine. We could say, what if I had gaseous CO2 here at this temperature, and I increased the pressure, holding the temperature constant? That'll be going straight up. We can see it would liquefy. When we can do any combination, we could say we could start here. What if we increase the temperature and then decrease the pressure? So we can predict what would the state of matter be, or find out at what temperature would it change. Or something. It's a useful figure for that. There's a point where the solid, liquid, and gas all intersect. This is called the triple point. The triple point's kind of funky. All three states of matter are present at the triple point in equilibrium. If you hold the right conditions right at that point, you have solid, liquid, and gas all present together, and all 6 phase changes. It's really weird when you think about it. It's almost information overload. It would be melting and freezing in different places. It would be boiling and condensing, evaporating and condensing in different places. The other phase changes, we've actually seen this one. CO2, solid CO2 is sold under the name dry ice. And we saw when I brought some dry ice in last week that it went directly from solid to gas. That phase change is called sublimation. The verb is it sublimes. The opposite process, gas to solid, is called deposition. The verb would be it deposits. Solid deposits from the gas phase. And that's also occurring, as well as melting, freezing, boiling, and evaporating. All 6 phase changes, different places, all equilibrium, crazy set of circumstances, but only at one combination of temperature and pressure. It has to be 57 below 0 Celsius and 5.1 atmospheres to have the triple point for CO2. If you changed either the temperature and or the pressure, you'd leave the triple point, right? At best, you'd stay on a line and have 2 phases. At worst, you'd just go into a region and have 1 phase. So only one very specific combination is the triple point. What's neat about the triple point, which makes it an easy thing to ask about, like if you have a phase diagram on an exam and it doesn't say solid, liquid, gas, because you got to recognize which one's which or something, because it's easy to remember which one is which, right? The liquid is always this wedge shape. The gas is what you have at very low pressures. The solid is what you'd have at either cold temperature and or higher pressures. You can figure out where solid, liquid, gas are. They're always in about the same place. The triple point pressure tells you what the lowest pressure is at which the liquid is stable. And so that's a neat thing to use the phase diagram for. It's an important piece of information. So this phase diagram is telling me that liquid CO2 is not stable at any pressure below 5.1 atmospheres. So this is why dry ice sublimes. At 1 atmosphere, the pressure in the room is about 1 atmosphere. It never goes it never goes much higher or lower than that, right? I mean, if the pressure were 2 atmospheres, we would be extremely uncomfortable, if not in bad distress or something, right? So 5 atmospheres, forget it. That's a lot higher. That's why dry ice sublimes. It's not stable to have liquid CO2. If I have 1 atmosphere of pressure and I have solid CO2 at this very cold temperature, it's going to warm and warm and warm and warm and go from solid to gas directly. No liquid. So any pressure below the triple point pressure, you can't have liquid. And then you as you see, you have sublimation if you're taking the solid and heating it. The other interesting point on here, the critical point, comes from, actually, the most important thing about the critical point is the temperature. I took notes in tons of meetings in New Orleans, and this thing worked flawlessly. I come to class, and yeah, I think it might be the room is the problem. I'll have to try it in a different room and see. The critical temperature is the temperature that corresponds to the so-called critical point. The critical temperature is the temperature above which the liquid cannot exist as a clearly defined liquid. Beyond that temperature, you have what's called a supercritical fluid. It is like a liquid in some ways, but like a gas in others. At these high pressures, the gas is not that gas-like. It's a very dense gas. It's almost liquidy. But it's not very liquid-like either because the particles have so much kinetic energy at this high temperature for the species it is. You get the supercritical fluid, which has certain interesting properties, but that smear of color there, where it's kind of green and yellow smeared together, that's why. It's showing it's not really a liquid and it's not really a gas either. It's this supercritical fluid. And the temperature is the key player there. The critical temperature is the most important. And then the pressure that corresponds to that point is called the critical pressure. And the point itself is called the critical point. But the critical temperature is the biggie among those. The critical temperature is the hottest temperature at which the liquid exists as a real, clearly defined liquid. Any higher temperature, it's a supercritical fluid or just a gas, depending on where you are. Some people worry sometimes about the solid liquid line. They say, that line has a positive slope, and if it kept going and going, it would overhang the critical point. And it looks like it could, right? If the graph were tall enough, and this is a cartoon graph. This isn't really to scale, and that's a good thing actually in this case. But you look at that, and maybe that line could overhang the critical point at some point. And the key to this is that line has a slope that's exaggerated. It's way exaggerated. The solid liquid line is nearly vertical in reality. It's never going to overhang the critical point. We don't know of any situations where it does. They slope it like they do in these graphs, these cartoons of graphs, so that you can tell it has a slope that's not infinite, that has a positive, nearly infinitely positive slope, but not quite. So you can tell it's not quite vertical, it has a positive slope. It's really almost vertical. So don't worry about the line overhanging the critical point. It would never happen. The interesting thing about that is that CO2 is like most other well-behaved substances. They have a 3-section phase diagram in that slope is positive. Water is a weirdo. Look at the other phase diagram and you notice the difference, right? The solid liquid line for water has a negative slope. And water is one of only 2 substances that do this. The other being bismuth, of all things, which, why bismuth? But that's what it is. Where this shows up is in a particular physical property. Let's say we had ice at 1 degree below 0 Celsius. And we're down here below, let's say we're even at 1 atmosphere. So right where the little blue dot is. And we increase the pressure on the ice. It's ice, right? We're in the blue section of the phase diagram, the solid. And we increase the pressure, holding the temperature constant at 1 below. We increase the pressure and the water would liquefy. Compare that to CO2. What would happen if you had liquid CO2 and you increase the pressure? It would solidify. Other substances would do the same thing, but not water. And when you apply pressure, you form the denser form. We decided denser was a word earlier. We weren't sure if denser was a word, but we decided it's a word. So you form the denser form when you apply pressure. So what this is telling me is for water, the liquid is denser than the solid, which is good because it is, right? That's what we know. Most substances, the solid sinks in the liquid. Solid iron sinks in liquid iron. The solid is denser than the liquid for almost anything except water and bismuth, which is a good thing, right? This is nice because this means that ice cubes float in your drink. The ice cap floats on the top of the Arctic Ocean. It's not always good, right? The icebergs float on the surface of the Atlantic. It's bad for Rose and Jack, or at least Jack. So ice floats on liquid water, and this is shown in the phase diagram. So if we asked on an exam, from the phase diagram, which, and it might not even say what substance it is, right? From the phase diagram, which is denser, the solid, the liquid, you can't tell. You can tell from the slope of the solid liquid line. If the solid liquid line is negative sloping like this, then it's like water. The solid is less dense than the liquid. So that's an important takeaway from that. And that's because if you increase the pressure, you form the denser version of the substance. So that's a neat takeaway from the phase diagram. Once you release the pressure, it will go back to being solid again. So that's the interesting thing is, you don't like, they say, does this help ice skaters skate? The fact that under the blades, the ice liquefies momentarily. Does that help the skaters glide and everything? It's probably happening too fast to make much of a difference. They've looked into that. You don't see trails of liquid behind the skaters, really. When you release the pressure, it will go back to being solid anyway. But there's no evidence that it really helps the skating at all. They're moving too fast for it to be that big a deal. It's just low friction of the ice, sharp blades. So they say it helps ice skating. There's not really any evidence of that. And I grew up a couple towns over from Nancy Kerrigan, so you have to trust me. No, you don't. All right. Although I did. So let's see. So going back on this diagram here and going the wrong way, and I keep going the wrong way. Oh, no, more the wrong way. Let's go back to this for a moment. We got that graph on the right, and we have, three substances, different structures, different vapor pressures. So obviously, the structure affects the vapor pressure in some way. We see that these two molecules that have OH bonds in them have lower vapor pressures than the other one that doesn't. So it looks like the OH bonds have something to do with it. Ethyl alcohol and water both have OH bonds. The ether does not. That seems to be important somehow. So you've got to consider the forces between molecules. So first of all, when we're considering the forces between molecules, you want to be able to compare them to the forces within substances that we call chemical bonds. So just as a recap of kinds of bonding you've heard of before. Ionic bonds, you've heard of those before, right? If you had chapter 9, you recall lattice energy. Lattice energy is a particular measurement that tells you something about the strengths of the ionic bonds. It involves the energy associated with the crystalline solid versus the gas phase ions. It's in chapter 9. If I had you last semester, you might recall, I think it's the topic where it came up that the most important thing in lattice energy, everything else being equal, would be charge. So if you remember that, the charge on the ions is very important. We're getting an organ installed where that old film projector is. It's going to be great. Nobody's used that film projector, and I've been here 16 years. So we're getting rid of that. We're getting an organ. It's going to be spectacular. We're going to have an organist, and we're going to do charge altogether. So if you recall, ionic bonding with lattice energies, few hundred to a couple thousand kilojoules per mole. Nice, healthy amount of energy that's given off when the bonds form. Or, if you like, that's the amount of energy that would have to be put in to break the bonds. Goes either way. So that's a nice, healthy amount of energy. And that's because of the force between the cations and the anions. Again, charge, holding the ions together. Covalent bonds. It's also charge. It's somewhat more nuanced. Instead of cation, anion, in-your-face charges, it's subatomic. The nuclei are positively charged because that's where the protons are. The electrons are negatively charged. So you get a pair of atoms. Each atom has a nucleus, and the nuclei attract the shared electrons, which are negatively charged, and that's what holds the atoms together. So Dr. Malik and everyone else in the physics department, they got all really excited because they say, see, it's physics. We told you, physics is really important. And that is true. We tip our hats to Ayer Hall that charge is important here as well. That's what makes covalent bonds occur is opposites attract, Coulomb's law, Paula-Abdul, attractions of opposite charges. Opposites attract, covalent bonds are up to 1,000 plus kilojoules per mole. Nice, healthy amount of energy. Metallic bonds, you might recall also, from chapter 9. You pool the valence electrons. The metal ion cores are attracted to the pooled valence electrons in the crystalline structure. And the energy of metallic bonds is, on average, a few hundred to up to 1,000 plus kilojoules per mole. So they're all in the same ballpark. Whether it's ionic, metallic, or covalent bonding, they're all in the same ballpark of energy, of hundreds to 1,000 or a few thousand kilojoules per mole. And those are the forces within substances that hold substances together, chemical bonds. For comparison, we can compare these to intermolecular bonds. Intermolecular means literally between molecules, right? The prefix inter means between. Now, it's easiest to take this. This is table 12.1 in the textbook. It's in the book. If you have the physical book or the e-book or whatever, it's table 12. I think it's table 12.1. 12.2, sorry, 12.2, but it's a table. I couldn't remember if it was a table or a figure. This is a table, even though it's got artwork. It's a table. Some things with artwork are figures, even though they are table-like, but this is a table. It's easiest to break the 6 intermolecular forces up 3 and 3 to think about, where the first 3 involve polar molecules. You might recall chapter 10 with the shapes of molecules. This also brings up chapter 9, electronegativity and stuff. If a molecule is polar, what that means is there's something enough about the molecule not being symmetrical enough with the bonds and the polarities of the bonds that there's a net positive-negative distribution in the molecule. So if you have, an oxygen molecule, O2, it's nonpolar. Both atoms have the same electronegativity. But a molecule of HF is polar because H and F have very different electronegativities. And you can do this with larger molecules as well, but let's just worry about simple ones for the moment. The bottom of the 3 here is easiest to look at first. Dipole-dipole forces. That name simply refers to the fact that both molecules have a dipole, which means they have a positive end and a negative end, 2 poles, like a magnet, but instead of north-south, it's the positive and negative charges. They have ICl, iodine monochloride, here. Iodine is less electronegative, chlorine is more. The color coding in all of the artwork here for this and above, as we see, is that negative is red, positive is blue. And that's in all the artwork in both parts of the table. So if I have an ICl molecule here where the negative end is the chlorine, partially negative, and the positive end is the iodine because it's less electronegative, another molecule, when it comes along, is going to try to get its negative end near the positive end of the first molecule. And it's not just 2 molecules in a sample, right? There's like a mole of them or something. So this is going to line up molecules. The one below is going to be red on the left, blue on the right. And there'll be ones in front and in back, all different sides. And they might be moving. So there's a lot going on. But that ... that's the dipole-dipole force. It's weak. Look at the energy. It's maybe a couple dozen kilojoules per mole compared to covalent bonds, which are like hundreds or thousands. So when you boil liquid ICl, what breaks? The covalent ICl bonds that are hundreds of kilojoules, or the dipole-dipole forces that are a couple dozen? The weak ones, right? So the weak forces break, of course, first. So the ICl stays intact as molecules, but the molecules separate. Ion dipole forces are worth mentioning. Those are primarily important when you have an ionic compound dissolving in water, like sodium chloride. The sodium ions are positive. So the water molecules will have their negative ends, where the oxygens are, attracted to the cation. The chloride ions are anions, so the positive ends of the waters would attract to those. And we'll see those again. We're going to see those again in chapter 13. We're not going to obsess wildly, especially right near the end. But ion dipole forces, it says, have energies from 40 to 600 kilojoules. A lot more of them are closer to the 40 than to the 600. Most of them are in the dozens. There aren't that many in the hundreds. So most of them are at the low end as opposed to the high end. Now the last one to mention, that's the tease for the next time, is hydrogen bonding. Hydrogen bonding is a crummy name because it's an intermolecular force. And we're going to do a lot more with hydrogen bonding. So don't sweat it if you're saying, gee, I don't understand it. You only said about it for a couple of minutes. We're going to talk a lot more about it a week from Tuesday. But hydrogen bonds are very important, and they occur whenever you have an oxygen, nitrogen, or fluorine bonded to H covalently, and then another NO or F atom elsewhere with a lone pair of electrons, at least one lone pair of electrons. So in this cartoon representation, A and B are both either N, O, or F. They don't have to be the same. That is to say, A could be nitrogen and B could be oxygen, for example. Or they could both be the same, doesn't matter. The NO and F are the most electronegative elements and the smallest. Chlorine's about the same electronegativity as nitrogen, but it's too big to do this. Okay, so that's why it's N but not Cl, even though they have the same electronegativity. So two water molecules. There's the OH thing, right? We saw ethanol has OH, water has OH. Here's why they have lower vapor pressures. Hydrogen bonding is very strong compared to other things. It's kind of the altoids of intermolecular forces. The OH group here can hydrogen bond with the oxygen on the next water, and this can be continued around a sample of water. And hydrogen bonds are in the dozens of kilojoules per mole. Curiously strong. Like I said, it's like altoids. So these are relatively strong forces, and this is going to be important because, as we'll see next time after spring break, if it weren't for hydrogen bonding, we wouldn't be here. And that's for a couple of reasons. Because of water would boil at 100 below Celsius, DNA wouldn't stay, the two strands stuck to each other. It's really important.